Good morning. Let us now see about JFET amplifiers. So the JFET amplifier, it provides an excellent voltage gain and high input impedance. Generally we have three basic configurations: common source, common drain and common gate. So here in the FET, field effect transistor, the output drain current is controlled by means of the input gate voltage. So the gate voltage will control the drain current. So this is a general N-channel JFET and its equivalence circuit, small signal equivalence circuit. So for the JFET amplifier, so here this is the equivalent circuit. Now let us see the analysis of common source. So here in the common source, we are now going to see about self bias and voltage divider bias. So here we are seeing about self bias. Here we are going to see about voltage divider bias. And we have bypassed condition and also unbypassed condition. So in the bypassed source resistance, so here we bypass with the help of a capacitor. So the voltage is being bypassed and it does not affect the gain. So if I don't bypass with the help of a capacitor, I'll have an voltage drop. So that drop need to be considered. Okay, this is a general circuit for self bias. And in the voltage divider bias, we have R1, R2, which acts as a voltage divider biasing circuit. So here we have coupling capacitor C1, C2, input coupling capacitor, output coupling capacitor. C2 is the capacitor which is used to couple the output. And the bypass capacitor CS. So it acts as a short circuit for low frequency analysis. So this is the equivalent circuit. We have gate resistance RG. We have gate resistance RG. This is the equivalent circuit of JFET. And we have drain resistance RD and load resistance RL. So the equivalent circuit of self bias and voltage divider bias are same. So here we have a fixed resistance, gate resistance RG, and here we have R1 in parallel to R2. So when coming to the circuit analysis, input impedance ZI, we have only one resistance RG, so that is fixed. So ZI is equal to RG. Let me consider it as equation number 1. The output impedance Z0. What are all the resistance present? Small rd, capital RD and load resistance RL. All the resistance are connected in parallel. So RD in parallel with capital RD in parallel with load resistance. So let me consider drain resistance and load resistance as RL dash. So I can replace RD parallel to RL as RL dash. So if my value of RD is greater when compared to RL dash, so here it is connected in parallel. So 1 by RD plus 1 by RL dash. So if my value of RD is very greater, so when 1 by RD, so the denominator value will be very less. So consider only RL dash. So my value of Z0 is equal to RL dash. Voltage gain is given by voltage gain AV is output by input, output voltage by input voltage, output voltage by input voltage VI. So from the equivalent circuit, what is output voltage? V is equal to I into R. So what is the total value of current here? Gm into Vgs is the current which is flowing, and resistance Rd in parallel to drain resistance in parallel to RL, load resistance. So when we calculate output voltage, current into the voltage, as the current is flowing in the opposite direction, I include the negative sign. Input voltage Vi, let me consider it as voltage across gain, gate and source voltage. So Vi is similar to the gate to source voltage VGS. So Vi, as they are parallel, Vi is equal to VGS. So substitute now in equation number 3. Voltage gain AV is equal to V naught by Vi. We know V naught is equal to minus Gm into VGS into GRD parallel to drain resistance and parallel to RL divided by Vi. Vi is VGS. So VGS will be getting cancelled, and hence I get minus Gm into Rd parallel to drain resistance and parallel to load resistance. If my value of Rd is greater when compared to drain resistance and load resistance, so this is connected in parallel. So 1 by Rd plus 1 by Rd plus 1 by RL. So if I consider Rd is greater, I should know that my value of Rd is very less. So consider only capital Rd in parallel to load resistance RL. So my value of gain will be minus Gm into Rd in parallel to RL. So let me consider this as RL dash. So the negative sign will indicate that the phase shift between the input and output voltages are 180 degree. So they are at a phase shift of 180 degree. The same thing we get using voltage divider bias. So next we can see about common source amplifier with unbypassed condition. So first we saw about the bypassed. So here in unbypassed, so I am not going to bypass this source resistance by using a capacitor. So there will be an voltage drop. So the gain will be affected. So I need to consider the drop in the equivalent circuit. So I have included the value of source resistance. So remaining all these are same. So this is the equivalent circuit of FET. I have included source resistance, Rd and RL. Now I know that input resistance Ri equal to Rg, output impedance Z0 dash. So my Z0 will consider, so whole this resistance I have considered this as Z0 dash. So Z0 dash in parallel with Rd in parallel to RL. So from the circuit, I know that Z0 dash, Z is equal to V by I. So here in the output, V0 by ID. So when I apply KVL on output circuit, what is my V0? So here I am going to apply KVL. Okay, so here current ID is flowing, ID into RS. So in here I need to calculate the current flowing through small rd. So we know the total current is Gm into VGS. So here the current ID is flowing. So the total current ID minus the opposite branch current Gm into VGS into RD plus ID into RS. I will get the output voltage. So if I apply KVL to the input circuit VGS I can write it as VG minus VS. So VG is my input voltage, so VI minus VS. What is V? VS, voltage across source. So the current ID is flowing, I into R, ID into RS. So if I substitute Vi is equal to 0, VGS value will be minus ID into RS. Now substitute this value of VGS in equation number 4 to find what is V0. So we calculate the V0 value, and now I need to substitute this V0 in equation number 3. So Z0 dash is equal to V0 by ID. So substitute the value of V0 in Z0 dash. So I get small rd plus rs into amplification factor plus 1. So what is Z0? Z0 is Z0 dash. So now I have found the value of Z0 dash. So here substitute that value of Z0 dash in parallel to RD in parallel to RL. So substitute, so we can find the value of Z0. So now we can find the voltage gain. So voltage gain is V0 by Vi. So I know that V0 is equal to minus ID into RL dash. V0 is equal to I into R. So the current flowing is ID into RL dash. So this is V0. So since I consider the current ID is in opposite direction, I mentioned as minus ID into RL dash. So substitute the value of V0 as minus ID. So from equation 4, V0 is ID minus VGS into RD plus ID into RS. So we are able to find the value of ID. So we are calculating the value of ID. So from the value of ID, I am going to calculate what is output voltage V0. Okay. So if I find output voltage, I can substitute in voltage gain. Voltage gain AV is equal to V0 by Vi. If I consider RS plus RL dash is very less when compared to RD, I can leave those both terms, consider only RD. RD will be getting cancelled. So the gain value is minus GM into RL dash by 1 plus GM into RS. So this is the analysis of common source amplifier using bypass and unbypassed circuits. Thank you.